In modern C++ programming, one of the most powerful features you will encounter is the standard template library known as STL, which is a collection of well-tested, reusable, and template-based classes and functions that are designed to help the developers handle the algorithms, the storage aspects, the manipulation with very ease and efficiency. Instead of writing data structures like stacks, queues, or linked lists from the scratch, we can use the ready-made, highly optimized versions in the STL. So STL is organized into three main components: containers, algorithms, and iterators. So containers are the data structures that store collection of objects such as arrays, linked lists, stacks, queues, vectors, maps, or sets. Algorithms are built-in functions that perform operations like maybe searching, counting, sorting, or transforming elements stored in your containers. Finally, the iterator acts as a bridge between container and algorithm, allowing traversal and manipulation of data without exposing the underlying structure. So together these components form a unified framework for managing data efficiently in C++. So the motivation behind STL is productivity and performance. It allows the programmers or developers to focus on solving problems rather than building a lower level data structures. So STL combines a generic, fast and tested library, and it also reduces development time while improving code readability. So STL provides a collection of ready-made type independent data structures built entirely using templates, and among these the vector container is one of the most widely used. It acts as a dynamic array, growing and shrinking as required without you worrying about the memory management. So you can think of a vector as a smarter version of an array. Unlike a fixed size array, a vector automatically resizes itself when new elements are added. It also provides a rich set of member functions for easy insertion, deletion, and traversal. Let's start with a basic example. We create a vector of integers using that vector int v. Then we insert values using push_back function. When we print, the output will be 10, 20, 30. So these are the vector elements. So notice how easy it is. No fixed size arrays, no manual memory management or handling. So the vector class provides several handy member functions. Pushback adds a new value at the end of the vector. Popback removes the last element of the vector and reduces the vector size. Size function returns the current number of elements in the vector. Clear empties the vector, in other words it changes the size to 0. Front and back gives access to the first and last elements. Then int function returns the value at a specific position in the vector. These make vectors extremely convenient and safe to use. Notice that we have seen how vectors work with simple data types. Let's explore how powerful they become when we use them with objects. In this example, we will store and manage a list of employee objects with an STL vector. Here we define our employee class, which has two private data members, name and pay rate. To allow input and output directly through standard streams like cin and cout, we declare two friend functions. Again, you can recall that concept that we covered during operator overloading, the overloaded insertion and extraction operators. This enables us to input and display employee objects easily, just like we do with the primitive data types. The overloaded operator, one that intends to print a employee value, so it outputs the name and pay rate in the formatted way, and one is used to read the data from the user, prompting for both the name and the pay rate. This makes our class more intuitive and integrates seamlessly with the C++ I/O system. In the main function, we declare a vector named myVector to hold employee objects. Each element of this vector will represent one employer record. We also declare a temporary employee variable, entered val, that we'll use to store input before adding it to a vector. Here the user is prompted to enter the details of one employee. After input, we use pushback to insert the object into the vector. The function size then tells us how many employees are currently in the list. Finally, we loop through the vector and print each employee using that overloaded operator. So this is a perfect example of object storage with automatic memory management, and the vector handles all the resizing and the memory allocation internally. So vectors allow random access to any element using either subscript operator or a cipher add function. So the add function checks whether the index is valid, preventing the accidental out of bound errors. So in this example, the user can enter a position and a program displays the corresponding employee record from the vector. The program successfully stores each employee as an object in the vector. You can add as many employees as you like, and the vector grows dynamically. So this shows the true power and flexibility of combining classes with STL containers. To summarize, vectors offer automatic resizing, fast random access, and easy insertion or deletion. They work beautifully with the STL components like algorithms and iterators, and since they are built using templates, they can store any data type. We have learned how vectors can store and manage collections dynamically, but the real magic begins when we combine the vectors with STL algorithms. So algorithms is a powerful built-in functions for transforming, searching, or maybe sorting with minimal effort. So we will now see how these algorithms work in hand with containers through iterators. Until now we have learned how to create and use vectors, even vectors of objects, to store and manage data. But what if we want to search and sort and manipulate this data efficiently? Do we need to write loops every time to process our container elements? Not necessarily. The standard template library provides a set of generic tools called iterators and algorithms that handle such operations with grace and efficiency. An iterator acts like a pointer that helps us to move through the container one element at a time. In this example, we create a vector named numbers and declared an iterator, it. The expression numbers.begin returns a iterator that points to the first element in the vector, while numbers.end function points to the one position past the last element. Inside the loop, we dereference the iterator using asterisk it to access the value it points to, just like dereferencing a pointer. This is how we can traverse the vector without needing to know its internal implementation. Iterators work not only with basic types but also with objects. Here we have a vector of employee objects. Each time we use it of name or it of pay rate, we are accessing the members of the object of the iterator is pointing to. We are accessing the members of the object the iterator is pointing to. So this makes iterators extremely versatile. They can navigate through any container and work seamlessly with user-defined types. Now let's make our iterator even more powerful by combining them with STL algorithms. STL provides a rich collection of some predefined algorithm functions that perform tasks like searching, counting, sorting, or modifying any container data. So these algorithms take iterator as an argument, which makes them work generically with any container, whether it is a list or a vector or a map. So in this example, we use find algorithm to search for a specific element. In this case, let's suppose a number 30. So the function takes two iterators, the beginning and end of the range, and the value to search for. If found, find function returns an iterator pointing to the found element. Otherwise, it returns the end iterator. Sort algorithm is another classic example. It takes two iterators, start and end of the range, and sorts the elements in ascending order. So the STL sorting algorithm is highly optimized, often faster than many custom written sorts. When working with objects, we can tell sort function exactly how to compare elements by passing a custom comparator function. Here compare by pay compares employees based on their pay rate. The sort function then automatically orders the employee list accordingly. So this illustrates how iterators, templates, and algorithms come together, allowing STL functions to work seamlessly with user-defined data types.